example 2.2.1. 2.2.1, and you might call this Newton's second law. And just as a reminder, what did we say about Newton's second law for those of you that never had to take physics? Which is, yeah, so we have kind of two different versions of it. We have a scalar version of it. So we say F equals m times a. And then we have a, I don't know, I might call it the net version. You know what the net version? The sum of all forces acting on an object is equal to mass times acceleration. And then we have what we call the differential, I might call it the differential version. Right? Which is the sum of all forces acting on an object is mass times the second derivative of the displacement function, right? And you might actually write that last one as m times the second derivative, ordinary derivative of u of t. This is called dot notation. Have you seen that before? Okay, it's engineering notation for the second derivative. You could think about it like chong chong, except it's not chong chong. It's double dot. So it's u double dot. That means the second derivative, or it also means the acceleration. And those are all different versions of how we realize Newton's second law, right? So in like physics 2a, we probably would do this one. By the end of physics 4a, we'd probably get into this one. And by the time we're in like dynamics, we think much more about this one, right? In statics, you know what often happens? This goes to 0. Why does that go to 0 in statics? Because it's static, aka there's no motion. You know what dynamics is? It's not 0. Yeah, motion. Okay, so let's take a look at this thing. So to calculate force of gravity, I don't know if it's on a mass or by a mass. I guess on a mass. M1, we say, let's call it F1 is equal to M1 times the acceleration due to gravity. And I'm so happy that Mike is here for many, many reasons. But one of them is to make sure that I'm doing this right. Okay, what do you know about multiplication? It's commutative. Okay, what is the force, what is the acceleration due to gravity? 9.8 meters per second squared, and then perhaps you call that M1. Okay, over there we had a mass matrix, didn't we?
The force is not 9.8, the acceleration is.
The acceleration due to gravity, I'm sorry, did I say force out loud?
Well, when you run down.
Oh, okay, so calculate the...
No, it wasn't. At the bottom row, at the one. What's the last row? Times n. Times n. Times n.
No, he replaced the a with 9.8.
Yeah, use this. Got it.
Oh, yes.
Am I off?
It's fine.
I'm tired right now, so I was up at 4:30.
You write the units, which is meters per second squared.
Yeah, this is the classic mathematician's trick, right? Confuse everybody, including themselves. Yeah, and then I suppose this would be kg, right? And then what is this? This would be newtons, and let's do the unit equation. So 1 newton is equal to 1 meter kg per second squared. Is that right? Yeah. So so I'm okay so far, right? Okay, so let's think about this. Do you remember in Hooke's law, we had this mass matrix? Do you remember it? Or the mass vector, I'm sorry, the column vector, which was the Hooke's law experiment. We took a spring, we hung a bunch of different masses off the spring, and then we had the M, right? Formally speaking, what did we say Hooke's law was? Force equals K times U. And then the forces here were the forces due to gravity, right? So we had a mass vector. How would we translate the mass vector into a force vector? So from Hooke's law experiment, we now have a way to calculate, this is now a calculation, not a measurement, forces based on masses. Okay, so what would we say? The force vector associated with different masses that were used is equal to what? 9.8 times the mass vector. So this would be 9.8 times what? M1, M2, all the way down to Mn. What is n? The number of measurements that we took, right? Okay. And then, of course, this would be 9.8 times M1, 9.8 times M2, all the way down to 9.8 times Nm. Each of those things is in what unit? Newtons. Right? Because they're forces.